we want to test the variances of the vitamin C content. I should write that here, vitamin of two different brands of vitamin pills. So we've taken a sample from each brand consisting of 5 pills, and we've measured the vitamin C content, and we would like to know if the two brands, the two populations of vitamin pills, these are the population, of whether they exhibit the same variance. So we'll refer to this sample as sample 1, and this is sample 2. So our null hypothesis is that, well, actually we're testing the ratio of the two variances. So the null hypothesis is that variance 1 divided by variance 2 is equal to 1, which is to say that they are equal. Now I don't have to choose the number 1 here, but if I want to test if the two variances are the same, then I have to choose 1, obviously, because that means the two are the same. So 1 is a very common choice for the hypothesized ratio. And the alternative hypothesis is, well, I'll choose the two-tailed test. So the alternative hypothesis is that the two variances are not the same. Right. So in order to test these hypotheses, we have to compute a test statistic that has a known distribution, and the one we need to compute is the F Test Statistic. It's the sample standard deviation of the first sample divided by the sample standard deviation of the second sample. This test statistic has an F distribution with n1 minus 1 degrees of freedom and n2 minus 1 degrees of freedom. So this F distribution has two sets of degrees of freedom, and they're given by the sample sizes -1 in each case. And it's very important that you keep the order. So this number of degrees of freedom refers to the numerator of the test statistic, and this number of degrees of freedom refers to the denominator of the test statistic. Now we can compute the p-value. The p-value is given by 2 times the minimum of two numbers. The first number is the cumulative F distribution with n1 minus 1 and 2 minus 1 degrees of freedom evaluated at the test statistic. The other value is the 1 minus the cumulative F distribution with n1 minus 1 and n2 minus 1 degrees of freedom evaluated at the test statistic. So why do we compute the p-value in this way? That's because the F distribution, well, there are lots of F distributions, but all of them have in common that they look kind of this way. They have a maximum at 1. They start at 0 and go towards positive infinity. If my test statistic is a positive number, let's say it's here, and it's greater than 1, it's always positive, sorry, but greater than 1, that's what I meant, then the p-value is given by this number here. So the probability excluded by the test statistic to the right of the test statistic, right? Further away from one. One represents the most, the value of the test statistic. If the two variances are the same, then that would be the most probable. This area here around 1 is the most probable interval in which we would get a test statistic. So if they are equal, then anything that's to the right of this number is more, or is less likely to obtain than what we actually obtained. If the test statistic happens to be less than 1, let's say here, then we're interested in this area over here. In this case here, this number here represented by this shaded area here is given by that number here. Whereas this area here is given by this number here. And we want a formula that's working for all cases, and that's why we have to choose the minimum of these two values, because it's always the small area that we're interested in. And then we multiply by 2 if it's a two-tailed test. So we get this area multiplied by 2 to get the p-value. Let's try to do it in Excel. So here we have the data. The first thing we compute is the sample standard deviation of the first sample, STD, and then DEV in English. And remember, it's the sample standard deviation. Same thing for the second sample. Then we compute the test statistic. It's this one squared divided by this one squared. So we get a test statistic which is smaller than 1. If I had divided S2 by S1, then we would have gotten an F0 which is bigger than 1. There's no rule. I mean, my choice is to say that this is the sample 1 and this is sample 2, but you could choose the other way around. That would give you a different test statistic. So that doesn't matter really. What matters is that you are aware of which one is the numerator and which one is the denominator, and then keep that order in the sets of degrees of freedom here. Okay, so let's compute the p-value. Well, that's equal to 2 times the minimum of, and then the first number is, I need the cumulative F distribution, so I'll write F, and in English I'm sure it's F dist, but in Danish it's F fordeling. And we insert the test statistic. The number of degrees of freedom is 5 minus 1 for the numerator here, and for the denominator, so that's this one, so it's sample 2, that's also 5 minus 1, but it doesn't have to be the same number every time. And we choose true, or in Danish cent, to get the cumulative distribution function. So that was this number here. Now we need this number, which is almost the same, except we have 1 minus. So I'll take a copy of this formula here and paste it into this one here, and then close the bracket. So we get a p-value which is roughly 84%, sorry. And if we have a level of significance which is 5%, then we cannot reject the null hypothesis, because the p-value is larger than alpha, way larger. It's important to note that to carry out the F statistic, the F test, we need to assume that the data has a normal distribution. Otherwise, the test won't work properly. If you can't assume a normal distribution, then there are other tests you can do, but I won't go through them here.